Hello everyone. Let us start with model number 4. It consists of 1D steady state heat transfer problems, or just it may be called as heat transfer problems. So in general, heat transfer is the transfer of energy from one region to another region due to temperature difference between the body, within the body, or between the body and the surrounding. So if the rate of heat transfer is constant with respect to time, it is called as steady state heat transfer. And if it is not constant with respect to time, if the rate of heat transfer is not constant with respect to time, it may be called as unsteady heat transfer. So the subject of heat transfer is of fundamental importance, and it is required to have the finite element formulation of heat transfer problem by considering the conduction, convection, and radiation heat transfers. So basically, there are three modes of heat transfer in terms of conduction, convection, and radiation. So conduction is the transfer of energy from one region to another through a solid medium due to temperature difference within the body or between the body and its surrounding. So the Fourier law of heat transfer due to conduction is given by Qx is equals to minus Ka dt by dx, where Qx is the rate of heat transfer in watts per meter square, K is the thermal conductivity in watts per meter Kelvin, and dt by dx is the temperature gradient in terms of Kelvin per meter. So, convection heat transfer is the process by which the thermal energy is transferred between the solid and the fluid surrounding it. And the rate equation is given by Q is equals to HA T minus of T infinity, where Q is the convective heat transfer rate in terms of watts per meter square, and H is the convective heat transfer coefficient in watts per meter square Kelvin, and T is the temperature of the surface of the body. T infinity is the surrounding temperature or atmospheric temperature. Uh, and lastly, the radiation heat transfer is the process by which the thermal energy is exchanged between two surfaces in the absence of a medium, and it is governed by Q is equals to sigma epsilon A into T minus of T infinity, where Q is the radiation rate of heat transfer in watts per meter square, and emissivity of the surface is given by epsilon. T is absolute temperature of the surface, T infinity is surrounding temperature, where sigma is Stephen Boltzmann constant and is expressed in terms of watts per meter square Kelvin to the power of 4. So in general, there are three modes of heat transfer in terms of conduction, convection, radiation, and the governing equation due to in case of conduction is expressed by Fourier law, and the governing equation in case of convective heat transfer is expressed by this equation, and whereas in case of radiation heat transfer, the rate equation is expressed by Stephen Boltzmann constant, Stephen Boltzmann equation, and is expressed as Q is equals to sigma epsilon A T minus of T infinity. So let us try to have the governing differential equation of the heat transfer problem, one-dimensional heat transfer problem. So let us consider a body, a one-dimensional steady state heat conduction with unknown field variable is temperature here. So the objective is to determine the temperature distribution in the wall. So the governing differential equation is derived according to the Fourier law. So a plane wall is considered, and in this an elemental length is considered of length dx, which is considered at a distance of x, and q is the heat entering into the body, and the rate of change of the heat entered is q plus dq by dx into dx, which is multiplied with the area of the wall. So here A is the area normal to the direction of heat flow in meter square. Q is the internal heat generated per unit volume. The heat flux Qx entering the plane wall in x direction is given by Qx is equals to minus Kx dt by dx. This is according to the Fourier law. And after changing a distance of dx, the rate of heat flux is q plus dq by dx into dx into the area. So this is the expressed after the distance of dx, that is heat flux at the x plus dx is q x plus dx is equals to minus kx dt by dx, plus rate of change of this. So net heat flux stored in the wall due to the conduction of heat along x direction is expressed as qx minus of qx plus dx. So this comes out to be kx d square t by dx square into dx. And we also know that from the figure, the internal heat energy stored. So energy stored, heat energy per unit volume is QA dx. So therefore, the steady state 1D heat transfer governing equation can be expressed as d square t by dx square kx a dx plus QA dx. Or in other words, it may be expressed as d by dx kx into dt by dx plus of q is equals to 0. So here is the governing differential equation. This equation is the governing differential equation for steady state heat transfer. If this Q is the internal energy is positive, if it is considered for the source or heat generated, and if Q is negative, it is called as sink or heat condensed. So if it is heat generated, Q is positive. If heat is condensed, then Q is negative. So basically, uh, governing differential equation is important aspect in this module. In addition to that, a few boundary conditions. That is, boundary conditions are specified temperature boundary condition. So looking at this location, T naught is specified and T infinity is specified. So T naught, if it is insulated, then at x is equals to 0, this T will be equals to 0. So at a distance of x is equals to 0, it can be expressed as T naught. And at a distance of length L, uh, it can be expressed as TL, which is equals to H TL minus of T infinity, which is convective heat transfer coefficient. So this is expressed with convective heat transfer coefficient. At a T x is equals to L, it can be expressed as HTL minus of T infinity. So looking at this figure, so at the innermost portion, it is completely insulated, and there is convective heat transfer coefficient at the right side. So outer surface, it is convective heat transfer coefficient, specified convective heat transfer, and on the inner surface, it is completely insulated, meaning that heat flux is 0 here, and we have to note the heat flux at this location. So the another boundary condition in case of a heat transfer problem is specified heat flux or convection boundary condition. So looking at the figure, heat flux is 0 at the innermost portion, and heat flux at x is equals to at x is equals to L is h into TL minus of T infinity, where TL is specified temperature at x is equals to 0, so that is at x is equals to L, and T infinity is the surrounding temperature, Q is the surface heat flux, and H is convective heat transfer coefficient. So there are two boundary conditions in case of the heat transfer problem. Basically, one is specified temperature boundary condition, and other one is specified heat flux boundary condition or convection boundary condition. In case of specified temperature, so we can express at x is equals to 0, it is T naught, and at x is equals to L, it is TXL, or Tx is equals to L, which is expressed as HTL minus of T infinity. And for specified convective boundary conditions, so it can be expressed as at x is equals to 0, Q is 0, that is heat flux is 0. At x is equals to L, Q is expressed as HTL minus of T infinity. So these are the two boundary conditions. Now, steady state heat transfer problems for 1D elements for conduction and convection problems. So basically, we have the same set of safe functions. So whatever we have in case of the problems, structural problems, wherein a member is considered as one single element. So at x is equals to 0, it is node number 1. At x is equals to L, it is node number 2. So the length of member is L, and the value of zeta in case of natural coordinate, it varies from -1 to +1. And here the intention is to find the temperature, whereas in case of structural problem, the measure requirement is to find the displacement. So in general, the safe function model can be expressed as n is equals to alpha naught plus alpha 1 zeta, And to determine the safe function n1, we have to express n as n1. n1 is equals to alpha naught plus alpha 1 zeta. Now we have to use the boundary conditions of node 1 and node 2 to determine n1 and also to determine n2. So first of all, to determine n1, at node 1, n1 is 1 as zeta is equals to minus 1. So we can express the equation 5.4.1 as 1 is equals to alpha naught minus of alpha 1. Similarly, at zeta is equals to plus 1, that is at node number 2, n1 value is 1. Yes, sorry, n1 value is 0. So there is slight correction. At node number 2, n1 is 0, zeta value is plus 1. So this need to be corrected, which is n1 is equals to 0. So we can express equation 5.4.1 as 0 is equals to alpha naught plus alpha 1. And if you solve equation A and B, you can get value of alpha naught as half, alpha 1 as minus half. So these values, when you substitute back in 5.4.1, we're going to get n1 as half minus half zeta or 1 minus zeta by 2. So n1 as 1 minus zeta by 2. So again, the same sketch variation we can show for a 1D element. Even to determine n2, we can use the same interpolation model, n2 as alpha naught plus alpha 1 zeta. We can use the boundary conditions of node 1 and node 2 for determining n2, and we can get n2 as 1 plus zeta by 2. So again, the relation between global and natural coordinate is written here, which is zeta is equals to 2 times of x minus of x1 divided by x2 minus of x1 minus of 1. So these set of equations, definitely these were considered in structural problem, and we have the same set of safe functions. We have the same set of interpolation model. The only thing, the field variable here is temperature, whereas in case of structural problem, the field variable is displacement. So to determine the strain displacement matrix, so strain here is considered as dt by dx instead of du by dx as in structural problem. So dt by dx, where t with respect to the distance x. So from chain rule, we can write this as dt by d zeta into d zeta by dx. And we know that from the expression of safe function, we can write t is equals to n1 t1 plus of n2 t2. So therefore, t is equals to n1 t1 plus n2 t2. We know the value of n1 and n2. They are safe function in natural coordinate as 1 minus zeta by 2 and 1 plus zeta by 2. So what we need in epsilon equation is dt by d zeta. So differentiating t with respect to zeta, we'll get minus t1 plus t2 by 2. And we also know the relation between the global coordinate and natural coordinate, which is expressed as zeta is equals to 2 times of x minus of x1 divided by x2 minus of x1 minus of 1. So what we need in epsilon equation is d zeta by dx. So differentiating zeta with respect to x, we get it as 2 divided by x2 minus of x1. x2 minus of x1 is nothing but the length of element. So x2 minus of x1, in general, it is x2 minus of x1 is considered as length of the element. So therefore, it is, we can write 2 divided by LE. So epsilon, when you substitute dt by d zeta and d zeta by dx in the equation, in this equation, so we'll get it as 1 by, minus t1 plus t2 by LE. When you get cancel this 2 from the numerator and denominator. So epsilon will be equals to 1 by length of element into minus 1 plus 1 multiplied with the temperature vector, which is T1, T2. So 1 by length of element minus 1 plus 1 is the strain displacement matrix, and the temperature vector, which is T1 and T2, is for that particular element. So epsilon is therefore can be expressed as V into T, and in case of structural problem, it used to express as epsilon is equals to B into U or B into Q. So epsilon is equals to B into T in case of thermal problem. So these equations, they absolutely remain same as that of the structural problem. The only thing I repeat again, the only thing here is the field variable is temperature, whereas in case of thermal problem, the field variable is the displacement. So let us try to have the finite element formulation of heat conduction using functional approach or variational approach. So in general, we know that to determine the stiffness matrix, we used to consider the strain energy stored in the member in case of structural problem. So to derive the stiffness matrix here, let us consider the total heat energy, that is potential energy functional in case of heat transfer, is expressed as pi is equals to 1 by 2 integration over the length L k into dt by dx whole square into dx. So here, in case of structural problem, this is expressed as E into dq by dx or du by dx whole square into dx. So the same thing is written here. Only thing here, instead of E, that is Young's modulus of the material in case of structural problem, here it is thermal conductivity expressed in terms of K. And instead of du by dx or dq by dx in case of structural problem, it can be expressed in thermal problem as dt by dx its whole square into dx. So this is corresponds to conductivity, and due to the internal energy, it is minus of integration over the length L qt dx, plus due to convection it can be expressed as half h TL minus of T infinity whole square. So it is required to remember the pi equation in case of thermal problem. It is expressed as pi is equals to half integration over the length L k dt by dx whole square into dx minus of integration over the length L qt dx plus of half h TL minus of T infinity whole square. The elemental stiffness matrix in general, as we have seen in structural problem also, this can be expressed as K is equals to integration over the volume V, B transpose dB into dV plus of integration over the area H n transpose n into dAs. So the students have to remember this expression. Even if you are not remembering the pi equation, you have to remember the K equation, because this is simplified by substituting the value of epsilon in this expression, and we get in general K as integration over the volume V, B transpose dV plus of integration over the area H n transpose n into d. So in case of thermal problem, it consists of conduction as well as convection. So the stiffness matrix is consisting of conduction and convection. So therefore, in case of one-dimensional problem, we can express over the volume as over the length L, and dV can be expressed as dx. So the same is written here. And we know that strain displacement matrix is 1 by length of element in the matrix of -1 plus 1. And transpose of this is 1 by length of element into a column matrix of -1 plus 1, where D is nothing but the thermal conductivity, which is expressed as K or Kx, which is thermal conductivity of the material. So when you substitute the B value here, so we'll get in general, and when we replace this dx as uh, 2 by LE. So that is, sorry, LE by 2. So this, we can use the relation between global and natural coordinate, which is zeta is equals to x minus of x1 divided by x2 minus of x1 minus of 1. That is 2 times of x minus of x1 divided by x2 minus of x1 minus of 1. When we differentiate that with respect to x, it will be 2 by LE. So we get in general as k is equals to akx by L in the matrix of 1 minus 1 minus 1 1, plus integration of this, we get it as plus of HAS in the matrix of 0 0 0 1. So this need to be understood. So conduction is there at node number 1, at node number 2 also, but whereas convection, so as per the sketch, the convection is there at node number 2 but not at node number 1. So we have to consider this convection term only at a 2 cross 2 entity. So whereas conduction is there at 1 cross 1, 1 cross 2, 2 cross 1, and 2 cross 2 entities. Whereas the convection is there at 2 cross 2 entity. So this is the thermal conductivity in case of thermal problem. So the load vector may be due to internal heat generation per unit volume, or it may be due to heat flux, or it may be due to convection. So as we are considering in the sketch only the convection, so there will be load vector due to convection, which is given by F is equals to in the matrix of 0 HTA into A. So you have to understand there is no load at node number 1 as it is free from the convection. So it is free from the convection or specified insulated, and we have the convection at node number 2, and which is expressed as HTA into A. This temperature of the atmospheric temperature or temperature of the body. So hence, the equilibrium equation in case of thermal problem is expressed as K into T is equals to F, which is AKX by L in the matrix of 1 minus 1 minus 1 1. This is due to conduction, and plus of HAS into a matrix of 0 0 1. So it is due to convection multiplied with the temperature vector consisting of T1 T2 corresponding to node 1 and 2 is equals to the load vector due to convection, which is 0, and HTA into A, where T is elemental temperature vector, K is thermal stiffness matrix, and F is elemental forcing vector. So you need to remember the shape function, you need to remember the stiffness matrix, and how to have the stiffness matrix in case of thermal problem, that you have to understand through variational approach. Straight away you can consider the elemental stiffness matrix, this equation, and by substituting the value of a B and B transpose, we can get a stiffness matrix of this type, right? So next it is steps involved in solving the numericals. First of all, we have to have the discretization similar to the structural problem, and we have to assume a temperature function if required. Then we have to use the stiffness matrix of individual element, and if there is axial conduction, we have to use this equation. If there is perimeter conduction, we have to use this, and if it is end convection, then we have to use this equation. In general, as what we have derived is for conduction, axial conduction, and end convection at node number 2 or at node number j. If there is perimeter conduction in case of the circular surfaces, we can use the this equation also, this matrix also. So in general, we use this, and load vector. In general, it may be for it may be due to the convection, or maybe perimeter convection, or end convection, or perimeter heat flux, or it may be due to heat flux at node J or internal heat source. So based on the requirement, we can use the load vector. If it is perimeter convection, we have to use this equation. If there is only end convection, then we can go for this. And if it is perimeter heat flux, we have to use this. And if it is heat flux from for node 2, then we have to use this. And if it is internal heat generated or internal heat source, then we have to use a load vector of this type, right? So these are the things which need to be understood. So there are different boundary condition as stated. Specified temperature boundary condition, can use specified temperature boundary condition, and specified heat flux boundary condition, and convection boundary condition. So once after having the stiffness matrix of individual elements, we have to have the global stiffness matrix and global load vector. And once we have the global stiffness matrix and global load vector, we can have the equilibrium equation in terms of Kt is equals to F. And once we have that, we can apply the boundary conditions, and the boundary conditions which we need to specify in terms of specified temperature boundary condition, specified heat flux boundary condition, and convection boundary condition.